Thank you everyone for joining, and Happy New Year. This is our first seminar of the year and our last of this series on space propulsion systems, taught by Professor Hiro Koizumi from the University of Tokyo. And yeah, as always, please keep your mics muted. There will be a chance at the very end for questions. You can either write them in the chat and we will read them at the end, or just wait and raise your virtual hand and you will have a chance to ask the questions directly. So yeah, Koizumi, whenever you want, you can take it away.
Okay, so let's go. So David, thank you for your introduction. So this is last session of my seminar. So this is the fourth one. So far, I have talked about the basic principle of the propulsion system and chemical propulsion and electric propulsion. And this time, I want to talk about the micro-propulsion, very small propulsion system. Okay. So let's go. This is today's outline. So micro-propulsion. So first, I want to start from what is micro-propulsion. And this is very simple, but yeah, I want to explain somewhat. And next, I want to talk about how to choose the best fit micropropulsion for your small satellite. So actually, recently, there are many candidates of micropropulsion systems. So when you try to use a micropropulsion system, you may be confused to select which one is the best. So here, I want to talk about some indexes for selection of micropropulsion system. And after that, as a third chapter, I want to talk about micropropulsion activity at my university, the University of Tokyo. So especially in my lab, we have developed several micropropulsion systems so far. So as an actual application of micropropulsion, I will talk about these micropropulsion systems. And finally, I will show you a lot of available micropropulsion systems. So recently, there are a lot of startup companies for propulsion systems, micropropulsion systems, and they are providing a lot of types of micropropulsion systems. So I have picked up several micropropulsion systems there. Then I will introduce those systems. Okay. So let's start from the very basic question: what is a micropropulsion? So its definition is very, very simple. So it's a very small propulsion system. And especially this is for small satellites, suitable for small satellites. So to understand micropropulsion, first we have to understand what is a small satellite. So this slide shows a categorization of small satellites. When you use small satellites, its range is quite wide. So in very wide meaning, when you say small satellite, it's a satellite less than 500 kilograms. And in that range, in the narrow meaning, small satellite means 100 to 500 kilogram satellite. So yes, I say standard sized satellite spacecraft, its size is about 1 ton or 2 ton or something like that. So in that sense, 500 kilogram is already small. And yeah, this range is sometimes called a small satellite. And also the size is going less than 100 kilogram. And sometimes we use microsatellites. In this term, usually we mean 10 to 100 kilogram satellites. And also when you go down further, less than 10 kilogram, they are called as a nanosatellites. And also there is another category or naming of small satellites. They are Cubesat. So Cubesat is a nanosatellite or microsatellite consisting of 1U unit. So here 1U, this is a kind of unit, 10 by 10 by 10 centimeters unit. And this 1U is original Cubesat. And if you combine several 1U unit, those satellites is called as, for example, 3U Cubesat. In this case, the satellite size would be a 10 by 10 by 30. And in the case of 6U Cubesat, the satellite size would be a 10 by 20 by 30 centimeters. So usually 1U to 6U Cubesat would be at nanosatellite range. And if it exceeds the size 6U, it may enter in the range of microsatellites. So I mean more than 10 kilogram. So this is one categorization of small satellites. But this is not so standard classification. Someone may use another definition of microsatellites or small satellites. So yeah, please pay attention about the accurate definition. But roughly say the small satellite is less than 500 kilogram satellites. And especially less than 100 kilogram they are microsatellite and nanosatellite. They are very easy to develop and cheap launch cost. And many institutes are interested in developing those microsatellites or nanosatellites. Okay, so those are definitions. And why we wanna make a microsatellites or nanosatellites? So this slide shows its motivation. So as you know, basically space development needs huge costs. So yeah, typical example is the cost of one satellite, standard size satellite. Usually it's cost about $300 million, so huge cost. And due to that huge cost, usually failure is never excused. Of course, at any cost, failure is not preferred. However, in this kind of huge cost, failure is never excused, I think. And due to that, sometimes, usually very conservative and long-time designs are used for the design of satellite. And of course, it leads to very long-time development and little growth of technology and human resource. And due to that, and to compensate that effect, we have to input more money. Then cost would be increased. This is one cycle, one negative cycle of the space activity or space development. Of course, this is not all of the space activity, but there is this kind of effect. And space development costs a lot of money. So the motivation of small satellites is basically to overcome that situation. So yeah, simply the satellite size is decreased. Rather than 1 ton satellite, 1 kilogram satellite can be cheaply developed and cheaply launched. So simply low cost development is very welcome for new players. And also quick technology cycle and its growth are expected. And this is also for human resources. Effective human resource development can be possible, can be achieved. So these are expectations for a small satellite. And as a result, rapid growth and innovations are expected. So micropropulsion is a propulsion system for those small satellites. And next, I want to talk about the basic features of micropropulsion. So there are two features. First one is a low performance, and the second one is a high dry mass ratio. So first, let's see first point, low performance. So basically, many propulsion systems are using hot gas or plasma, high energy state of material. And when you miniaturize the system, scaling down leads to shorter time for reaction and higher surface ratio. So yeah, first one is very simple. If you decrease the size from this one to this one, the time that one particle exists inside a certain area becomes shorter. And in the case of combustion, maybe reaction can be insufficient. So some uncombusted material would be ejected. Well, in the case of plasma, some particle would be ejected before the ionization. So this kind of reaction can occur in the miniaturization. And also, next one, higher surface ratio. So in any cavity, for example, when you produce a plasma inside a cavity, these surface becomes the cause of loss. So ions and the electrons are going to walls, and these are become loss. So this is a plasma loss. And to compensate the loss, we need to input the power and generate additional plasma. This is almost same as also for photogas. So walls are the cause of heat loss. So basically, when you miniaturize the system, scaling down, basically energy loss is increased, and as a result, thruster performance is decreased. This is an essential feature of micropropulsion systems. And the second point, maybe this is more important. So high dry mass ratio. So here, dry mass, I mean the mass other than propellant for propulsion system. So when you see standard propulsion system like this, usually most of the mass of propulsion system is propellant. So if you have a 100 kilogram propulsion system, maybe 80 kilogram or 90 kilogram of the mass is propellant. This is a standard case. But in the case of micropropulsion, often this dry mass ratio increases much. For example, 50% or maybe more than 50%. So this is because due to the miniaturization, some components are scalable for that miniaturization, like a propellant or tank itself. However, there are a lot of non-scalable components. For example, gas components. I mean, valve or tube or fitting, sensors or those kind of things. Usually, even if you reduce the scale of a propulsion system to 1/10, those components, those size cannot be decreased to 1/10. So easy example would be a screw. So usually, when you develop a propulsion system, standard propulsion system, you may use M4 or M3 screws. These screws are used. But when you downscale the size to 1/10, do you use M0.4 or M0.3? Usually it's impossible, difficult. So even if you scale down the propulsion system, for example, in the case of the screws, you have to use M3 or M2 screws. And associated with this screw size, structure size also is not scaled down. So we cannot develop a 1/10 size of all of the things. I mean, wall thickness or cavity size. And also here, controller. Controller is an interface between satellite and the propulsion system. And basically, that function is the same for standard size propulsion system and for micropropulsion system. So usually, this kind of device cannot be miniaturized even in micropropulsion system. So due to this component, basically dry mass fraction becomes higher. And due to that, what happens is ISP, or effective exhaust velocity, has lower meaning. So the meaning of ISP is a ratio of total impulse and the propellant mass. And in the case of ISP, we have to multiply gravity constant G. But the important point is this propellant mass and total mass ratio. And why this ISP is important is propellant mass is dominant in propulsion device. Then this ratio is very important. However, in the case of a micropropulsion system, typically this dry mass cannot be negligible. So instead of standard ISP, sometimes system ISP is used. The definition is almost same, but the difference is here. Not propellant mass, propulsion system mass. So total impulse versus whole mass. So when you look at the micropropulsion system, maybe on the data sheet you will find the specific impulse ISP. However, that value does not have a much meaning as standard propulsion system. You have to pay attention for system specific impulse or just a total impulse and also total mass of the propulsion system. So this is the second point. Okay. So micropropulsion is just a small propulsion system and so suitable for small satellites. And as I said, this is a classification by the size. So this means any type of propulsion system, any type of propulsion can be used for micropropulsion. So in second and the third session of this seminar, I talked about the chemical propulsion and electric propulsion. So all of the propulsion appearing there can become micropropulsion system. So a lot of candidates. And so if those are miniaturized and for a small satellite, this would be a micropropulsion system. And I think this for a small satellite is very important. So micropropulsion is not just miniaturization of a standard propulsion system. Typically, this is for a small satellite. And micropropulsion should be designed to fit for the purpose of a small satellite. Okay, next chapter, I want to talk about how to choose the micropropulsion system suitable for your satellite mission. Okay. So before that, first, please let me start from the history of micropropulsion or microsatellite. So roughly from 2000 to 2010, this period is a dawn of small satellites. So actually, the first Cubesat successfully operated in space was launched in 2003. And it was University of Tokyo's Sci-4 Cubesat, this one. And following to this Cubesat, a lot of institutes, universities, and companies started to launch and operate Cubesat or microsat or non-satellites. So this period is known by the birth of small satellites. However, on the side of propulsion system, this period can be called as dark age, because in this period, the technology of small satellites were not matured so much, and they didn't have a space to install propulsion system. So basically, in this period, most of small satellites didn't have any propulsion system. And you see that no propulsion, no freedom. You cannot change the orbit, you cannot adjust the orbit. So this period is a birth of small satellite, but for propulsion system, it's a dark age. And after that, after 2010, the rise of micropropulsion, especially for me. So small satellite technology were matured, and they have got space to install propulsion system. So applications and demonstrations of micropropulsions started. and many startup companies were born. And now, so after 2020, now we got a lot of selections. So what happened? So of course, good point is now we have many choices. So you can choose a propulsion system that would be best fit for your mission. So it's very nice. However, there's a disadvantage. That is this one. Too many choices. So you may be confused to choose the best propulsion system for your mission. So from now, I want to talk about some parameters you have to pay attention. So when you think about the micro-propulsion system, when you try to select a propulsion system, you may consider these kinds of parameters: thrust, ISP, size, mass and volume, and power consumption. These are very basic parameters. But when you look at these parameters, you have to pay attention to a lot of things. So I want to talk about those. So first, about thrust and ISP. These are very basic parameters. And basically, if you find the data set of a propulsion system, immediately you will find these values. But what you have to pay attention to is how they obtained these values. This is very important. So is it measured one, or is it calculated one, or is it expected one, or just they said so? So these are very big difference. So yeah, of course, the most reliable method would be the in-space operation. So in space, they operate the propulsion system and they actually change the orbit. And from this orbit difference, they can estimate the thrust. So this kind of information would be the most reliable one. That propulsion system will work in space and actually they will generate thrust. So perfect. But space flight is not so easy, and in many cases a ground test, especially under development, we measure thrust on the ground test, and we have a lot of methods to measure the thrust. So in the case of chemical propulsion, usually we use rotor cell force transducer to measure the thrust, and in the case of electric propulsion, their thrust is quite small. So usually we use a thrust stand. It's like a pendulum that installs the propulsion system on that. And by measuring the displacement of pendulum, we can estimate the thrust. So this is also very good method. And also sometimes we calculate the thrust from the other quantity. Here I mean, for example, current or pressure. So in the case of chemical propulsion, combustion chamber pressure is a very important index to estimate the thrust. From the pressure and nozzle size and nozzle coefficient, we can estimate the thrust quite accurately. And also in some electric propulsion case, by measuring the ion current, we can estimate the thrust. So in some devices, this calculation has also reliability. But some propulsion system, maybe its thrust may be expected only by theoretical values. So in this case, you have to care about its reliability. Usually, only theoretical prediction has very poor accuracy, and maybe plus minus 50% or 100% uncertainty exists. And also, sometimes they just say expectation. They want this kind of parameters for thrust or specific impulse. So sometimes those numbers are appearing on the data sheet or their plan. And also, without any proof, they just say those numbers. So even if you find these numbers, you have to consider about its source carefully. And the second one is a mass and volume. This is also very basic parameter, but you have to care that does it include all of the mass and volume of the propulsion system. So basically, propulsion system consists of thruster head, of course, but other than thruster head, we need propellant management system to control the flow rate. And of course, we need a propellant itself and its tank and power processing unit. This is basically for electric propulsion. So in the case of electric propulsion, we use high voltage or RF or microwaves. So we need a power processing unit and also controller. As I said, this is an interface between satellite and propulsion, and to operate a propulsion system, we need this one. So the described mass and volume is including those all of the things or not. This is also very important, especially in the research phase. Usually researchers are interested in only this thruster head. So they are focusing on thruster head, and they just mention the size and the volume of the thruster head, and they are not talking about other components. So in this case, usually this fraction is much smaller than others. Usually these parts are dominant. So if you are interested in, if you focus only on this thruster head, the size would be much different from the actual propulsion system size. And finally, power consumption. So again, you have to pay attention about, does it include all of the powers? So this diagram shows a microwave ion thruster case. So we have to operate ion source and neutralizer. And to generate plasma in ion source and neutralizer, in this case, for example, we need a 2-watt microwave power and a 2-watt microwave power. And in total, we need a 4-watt microwave power. And this microwave power is generated here, microwave power supply. And usually, or always, this kind of power supply has loss. So output is 4 watt. However, input may be 8 watt. So there's a difference. Also, for ion thruster, we need a high voltage power input to accelerate ions. And yeah, in this case, in this example, this might be 15 watt, but input for power supply may be 20 watt. And also we need a power for controller. So usually this kind of tiny power for controller can be negligible for standard size propulsion system. However, in the case of micropropulsion, this is not negligible. So we have to consider these powers. And in this case, in this example, the total power is 32 watt. So if you focus on only ion thruster or ion source, this is just a 70 watt. So there is a very big difference. So you have to pay attention to these things. Okay, so these are basic 4 parameters. Then enough? Not yet. So these are important thruster performance parameters. However, when you install your propulsion system to a satellite, you have to take care of other parameters like this. They are not directly related to the thruster performance, however, very important indexes. So first one is the power dissipation. So this is very similar with power consumption, but a little bit different. So power consumption is an input to propulsion system, this one. And this amount is very important, of course. But propulsion system uses this power, and some power is used for the kinetic energy. This is the main energy purpose of propulsion system. And some energy is used as a frozen loss, so hot gas temperature or plasma state. So these high energy state consumes energy. So these are called as frozen loss. And also hot part of the propulsion system emit radiation to outside. And due to those, energy is going out. However, all of the power is not going out. Some power is returned to the satellite. This is power dissipation. And due to that, we have to we have to manage this power dissipation. Especially in the case of micropropulsion, this fraction is quite large. As I said, essentially micropropulsion's performance is lower than the standard sized one. So this fraction is higher. And additionally, in small satellites, scale is small. So thermal insulation, its effect is lower than the big scaled satellite. So thermal insulation is more difficult. So we have to take care of these power dissipation, especially if you employ very high power electric propulsion. This power dissipation sometimes become very critical problem. So be careful about this. And the second one is maybe this is the most important handling of propellant. So handling ability of propellant becomes very important. So can you fire the propulsion system in your vacuum chamber? So usually under development, during the development, you wanna check the status of propulsion system. And you may want to fire your propulsion system by using your facility. However, some propellant, for example, toxic propellant or explosive propellant or corrosive propellant, those kind of propellants sometimes does not allow you to conduct this kind of experiment. And also this is the same for drain and refill. So if you use propellant on the ground test, of course, you want to refill the propellant, but is it possible? No. And also more simply, can you store it in your facility? Some materials like explosive, there are a lot of regulations about it. And maybe you are not allowed to store that in your facility. So in this case, it becomes a very big problem. And also transportation, especially to launch site or test site. By using land or sea or air transportation, some dangerous materials have a lot of regulations and your activity might be limited. And finally, for the launch, you have to pass the safety review and your propellant is okay for that. So propellant, its type may limit your activity more than expected, I think. And in the case of a traditional satellite, standard size satellite, they have a lot of knowledge and heritage for these kind of handlings. So in the case of ESA, NASA, or JAXA, they have a lot of heritage and knowledge. Then they can manage to handle those propellant. So for them, they would not be a big problem. However, for small satellite users, like a student in university or new startup companies, players, sometimes these becomes very high hurdle, big problem. So we have to take care of these so much. So I say this is not impossible to avoid these issues. And actually, if you are in NASA, they have a lot of knowledge about these. However, if you are in a startup company, new company, maybe this becomes a problem. So we have to consider these points, especially for the propellant type. And the next point is a contamination from the plume. So propulsion emit propellant to outside, of course. And sometimes there is a direct impingement, direct collision. Especially when satellites uses a very big solar array panel, and depending on the configuration of the thruster, some plume may hit the panels or antennas, those kind of points. Usually, we avoid this kind of design, and this hardly happens. However, here, collisional backflow, this always happens. So any propulsion system's plume has a collision inside that, especially in the chemical propulsion, its density is high. So there's a collision inside, and that collision generate backflow. That amount of backflow is not so much as main plume. However, tiny amount of backflow may cause a problem, especially that propellant is a it has a very low vapor pressure. It means it can be easily condensed. Or if that propellant is very reactive material, tiny amount of backflow becomes a problem. So we have to take care about this. And finally, electromagnetic interference. So yeah, this is typical for electric propulsion. So electric propulsion basically uses high voltage, and sometimes high voltage breakdown occurs inside the power processing unit or outside. And depending on the thruster type, the voltage is different. In the case of Hall effect thruster, typically 300, and ion thruster 1 kilovolt, and in the case of FEEP or electrospray 5 kilovolt. And higher the voltage, the more risk for this kind of breakdown. And also, some electric propulsion uses RF or microwave, and these leakage also can become problem, and especially with the interference of communication devices. So we have to check those interferences. Okay, so these are indexes I explained here. So when you select a propulsion system, you have to care about the total performance, not only thruster performance, not only these. You have to total effect. Okay, next, I want to talk about the micro-propulsion system developed in our laboratory, our university. So in my laboratory, we are studying and developing a number of micro-propulsion thrusters, and one of the those micro-propulsion thruster is this gridded ion thruster, small gridded ion thruster. So yeah, mainly it was developed, studied in 2007 to 2012, and you see the performances of this thruster itself. And the remarkable point is here power, so 12 watt for thruster itself. And this power is quite small as an electric propulsion, and yeah, this was the main purpose of this development. So to be fit for the small satellite, here we cannot use a big power, so we wanted to decrease this thruster power. So we developed this ion thruster, and after that we developed a propulsion system for actual microsatellite project. So you see, this is a propulsion system. You see the big tank, and this is a thruster head, and this is a microwave power supply, and gas management system. And in the bottom area of this system, there is a high voltage power supply and controller. So the total mass is 8 kilograms. So I think compared with today's propulsion system, this propulsion system is quite a big one. But at this moment in 2011, this was the smallest ion propulsion system, I think. And actually, we operated this ion propulsion system in space, but I think as a miniature ion thruster, this was the first operation in the world. So by using this for small satellite, we succeeded to fire the ion thruster in low Earth orbit. And following to that project, we started another micropropulsion project for PROCYON. This is a satellite name, and this is a 50 kilogram class microspace probe. So actually, it's not a satellite, microspace probe. It's going to the interplanetary orbit, so departing from the Earth. So it's orbiting around the Sun. And this was in 2015. And in this project, we needed RCS thruster. This is a thruster to control the angular momentum of the satellite. And also we needed the ion thruster here. So almost this satellite is has a almost same size as a previous one, this one. However, for this PROCYON, we needed to equip a lot of RCS thrusters. And to realize that, we selected this thruster, cold gas thruster, xenon cold gas thruster. So cold gas thruster has very poor performance. Actually, ISP is a 24 second, maybe the poorest performance in any type of propulsion system. However, due to its simplicity, it has very high reliability. So you see, this cylinder is a valve, and this is a thruster. And here, I cannot identify, but there is a very small nozzle. And the good point of this cold gas thruster usage is gas sharing. So in this slide, you see the component diagram of the micro ion propulsion system installed on HODESH-4 satellite. And basically, there are 4 components: controller and gas system and power supplies and ion thruster. And for PROCYON, we added cold gas thruster here, but we shared gas system and controllers. And this reduced the total mass and volume of the propulsion system. So we named this system as a unified propulsion system. So ion thruster and cold gas are unified. So I think this kind of unified propulsion system, or in other words, multi-mode propulsion system, is very useful for small satellite or micropropulsion, because when you use a propulsion system, its role is not only one. Usually there are some roles. And depending on that roles, your propulsion choice would be different. So sometimes you need a high specific impulse, and sometimes you need a multi-axis thrust, like an RCS thruster, while sometimes you need a high thrust. So to satisfy these requirements, if you installed 3 types of propulsion system, the total volume or mass becomes very big, and it will not be suitable for small satellites. Then this multi-mode propulsion or unified propulsion concept becomes very effective. So by sharing some components, we can reduce the total mass or volume. So in the case of PROCYON, we combined ion thruster and cold gas thruster by sharing the gas. Well, this is another example, Argon satellite. They combined green monopropylene thruster and cold gas thruster by using the plenum gas. So plenum gas means this gas is used to push the green propellant into the combustion chamber, and also they used this gas for the cold gas thruster directly. So this kind of dual usage of propulsion propellant is very effective. Okay, anyway, we succeeded to operate our propulsion system in space for 1 year. But during development, I felt big difficulty for the development. I mean, so the total propulsion mass of our system was 10 kilograms. However, propellant mass was just 2.6 kilograms, just 25%, 26%. And half of the mass was by high pressure gas system. So I wanted to reduce this mass, especially when we install propulsion system to Cubesat, we have to reduce this mass much. And also this kind of high pressure gas system has another problem. So a lot of regulations, and due to those regulations, we cannot design the original gas tank or high pressure components, and it leads to the high mass, heavy mass. And also for the launch, we have to pass a lot of safety reviews, and high pressure usage make it difficult more. So of course this is very important, but if it can be avoided, I want to avoid. So as a next step of this propulsion system, we begin to focus on the water propellant. So water is, as you know, it's a liquid in room temperature and pressure, and apparently it's very safe. And also in the future, in the near future, in-site resource utilization may be realized on the Moon or Mars. And in that case, water becomes a very attractive propellant. So now we are studying water ion thruster and water Laserjet thruster, and also water combustion thrusters. And in these three thrusters, this first one and the second one, we are developing propulsion system. So first, I want to talk about the water ion thruster. The operation is very simple. Instead of xenon, we are using water vapor, and its feeding is also very simple. So by using the saturated vapor, we can simply feed water to the thruster. And the plasma is a water plasma, and it includes H2O plus and H3O plus, or OH plus or O plus. But mainly H2O plus is a dominant. And as to the water Laserjet thruster, yeah, this is also very simple. We just eject water vapor. But one unique point of our thruster is this room temperature evaporation of water. When you hear the water vaporization, you may imagine 100 degrees Celsius. But by decreasing the pressure, you can vaporize the water in much lower temperature. And we selected this temperature. So we decrease the pressure down to the 3 or 4 kilopascal, and we evaporate water at this temperature. And the merit of this low temperature evaporation is low heat loss. So if the vaporization chamber, its temperature is high, the heat will escape to outside. But if this temperature is low, no heat loss to outside. Or maybe heat is coming from the outside. So in satellite, there are a lot of components, communication and OBC or a lot of components. And most of the components dissipate powers. And by setting the temperature at this low value, we may use those wasted heat from other component. And actually, we have developed two propulsion systems by using this concept. That propulsion system is called as Aquarius, and Aquarius 2.5U and Aquarius 1U. And one of the propulsion system was installed in a 6U Cubesat, EQUULEUS, this 6U Cubesat. And this EQUULEUS was now installed on the SLS, NASA's very big launch vehicle. And this year, we are waiting for the launch. So this is a flight model of our satellite. And you see here our propulsion system. And now this flight model was shipped to the US, and now it's waiting the launch. And additionally, now we have developed equivalent propulsion system, basically same design propulsion system, this one. And by using this equivalent model, now we are trying the operation. So combining with other satellite components, we are conducting operational training. Okay, and additionally, some graduate students from my lab and who was a main core member of this project founded a new company last year called as Pale Blue. So we have several experiences of small satellite project, and based on these heritage and knowledge, we founded a new company. And currently, they are providing water-based thrusters. So this one is a Laserjet Thrusters and ion thruster, and third one is a hybrid thruster. This means a hybrid of resistant ion. So this is a multi-mode propulsion system. So it can, it has a Laserjet here and at the center ion thrust. And also compared with the previous ion propulsion system, you see this propulsion system, its size is much decreased. Yeah. Okay, so finally, I'll talk about the available options of micro-propulsion system as of today. Okay. So yeah, these days, as I said, there are a lot of choices for micro-propulsion system. And here today, I have brought several propulsion system candidates, but they are not all. They are just propulsion system I have picked up this time. But maybe they are very useful information for satellite engineers, especially. So there are a lot of types of propulsion system. So first, I want to start from the cold Garches thruster. So this is a simplest principal thruster. And here you see 4 types of thrusters. And in the case of a cold Garches thruster, main feature is ISP. Usually it's less than 100 seconds. And the thrust usually ranging from 0.1 millinewton to 10 millinewton range, like this. And also not so much power consumption like this. And this is other parameters. Yeah, you see the size here. So all of these examples are 3 examples here. They are almost 1 use size. So it's suitable for Cubesat. And another one is a big one, but due to this size, it generates higher total impulse here. So this total impulse is simply depending on the mass of propellant. So if you increase the mass, you can increase the total impulse. And also remarkable point would be a propellant. Yeah, here Bhutan, and this is how to say, it is liquid gas. Sometimes, typically used for the extinguisher or those kind of things. So liquefied gas. And by using liquefied gas, by using low pressure, we can contain high mass in a certain volume. And also, this iodine is also, remarkable propellant. So in room temperature, it's a solid. But increasing the temperature of this iodine solid, we can evaporate the iodine to the gas state and we can eject it out. But of course, we need power to warm up the iodine solid. We need power, and this power limitation leads to the low thrust. So in this case, if you want to increase the thrust level, you have to increase the power consumption. So these are examples of Garches thrusters, and these are features. Yeah, the most remarkable feature would be high reliability. Very simple, the most simplest principle. So higher reliability. But its exhaust velocity is not so high, typically less than 80, and thrust depends on the flow rate. And typically, liquefied gas or sublimable solid used for Cubesat usage, microsatellite usage. And also, good point of Garches thruster is that multi-nozzle configurations are easy. So you see, yeah, here for thrusters, and I'm not sure, but yeah, this propulsion has also multi-nozzles. In this case, just a single, but in this case also we can install multi-nozzle configurations. Okay, similar with Garches thruster, next is Laserjet Thrusters. So only the difference is heating up the gas or not. So basically, features are same as a Garches thruster. Only the difference is here ISP, slightly higher than Garches thrusters. So here in this example, it's ranged from 70 to 180, a little bit higher. And thrust is almost same range, but it depends on the power, of course. And yeah, difference you see here, power consumption. Basically, power consumption is higher than the case of Garches thrusters. And this is the size and propellant. SO2 and again liquefied gas. And also, yeah, remarkable point is here. You see many thrusters are using water as propellant. As I said, water is very attractive propellant in the point of safety and handling ability, and also future in-space usage. And yeah, here all of the components are Cubesat compatible, and the total impulse is ranged from the 100 to 1000 Newton second. So if you want higher impulse, higher specific impulse than Garches, Laserjet become a candidate. But you have to prepare this electrical power. Okay, next is a monopropylene thruster. This is a typical chemical propulsion thruster. And the remarkable feature is that, yeah, ISP is much higher than Garches and Laserjet. And also thrust is higher. So in this case, we are using the chemical reaction. So we have much energy source. Then we can increase the ISP and the thrust like this. Power range, yeah, it depends on the propulsion type, but yeah, it ranges from 10 to 50 watts or something like that. And this is a propellant and the size and total impulse. Yeah, total impulse is much higher than the previous ones. And yeah, propellant, yeah, green propellant. These are all green propellant, so-called green propellant. Okay, so monopropylene thruster. Yeah, compared with cold and Laserjet thrusters, its performance is very attractive. However, in the point of difficulty, its difficulty is higher than previous examples. So you have to pay attention about it. I mean, you have to carefully check the status, development status of these thrusters. Is that technology is really matured or not yet? Is do they operate those on the ground test or in space or just designed? So these are very important. So compared with previous result, it can be called as an emerging technology. But here they are appearing. So very, very promising. And the next one is a bipropellant thruster. So in the point of technology, this is more difficult than monopropellant. So the number of candidates is fewer than previous ones, but there are some. So in this case, two examples, and higher specific impulse and higher thrust. And this is a propellant and the size. And of course, bipropellant thruster, we need a two type of propellant, like this or like this. Okay, so if you want higher specific impulse, this can become a candidate, but still its technology level is not matured, I think, especially compared with monopropellant thruster. But maybe within a few years or 10 years, this technology might be improved much more. And the next candidate is Electrolyte Thruster. This is quite unique thruster. So actually, when you focus on its acceleration phase, this is a bipropellant thruster. So it uses hydrogen and oxygen. And they combust those two gases. And they generate hot gas and exhaust it to outside by using the nozzle. So this is a chemical propulsion acceleration process and bipropellant. However, this hydrogen is generated from the water, liquid water, and also oxygen. So by inputting the electrical power to liquid water, we can decompose water to hydrogen and oxygen. So this is electrolysis. And accumulating these hydrogen and oxygen inside the tank, then we can combust those. So when you focus on this phase, apparently energy source of this propulsion system is electrical power, this power. And operation of this thruster is limited by this electrical power. So in this point, this is clearly electric propulsion. So energy source is electrical power generated by the solar array panel. So yeah, it's a combination of chemical and electric. Energy source is electric, but acceleration process is chemical. But yeah, anyway, very unique and interesting thruster. So sometimes it's categorized into chemical and sometimes it's categorized into electric propulsion. And also another important point is average thrust is very important here. So from its principle, it's accumulates the gas into the tank, and after that, it combusts that gas. So operation mode is a pulsed operation mode. So, but its pulsed frequency and the total impulse is limited by this electrical power. So you have to consider the orbital average thrust. So this value is orbital average thrust. Instantaneously, if you focus on the short time, it generates much higher thrust. Actually, it just generates 10 Newton or something like that in a few seconds, very short time. But average thrust is a essential parameter for this propulsion system. Okay, next example is more electric propulsion, like so Hall effect thruster. So I picked up 4 Hall effect thrusters, and 3 of Hall thrusters are quite high power, or more than 200 powers. So basically, Hall effect thruster, it is not so easy to miniaturize or to decrease the power. So it has a very good performance in high power range, and to decrease that power is somehow difficult. But recently, low power Hall effect thruster is beginning to appear like this. And specific impulse is, yeah, of course, this is electric propulsion, and it's much higher than the chemical ones, over than 1,000 seconds. And the thrust level is 1 to 10 millimeter range. And also, important point is, so for these three examples, I could not find the propulsion system size. On the data sheet, they are describing the mass of thrusters, about 1 kilogram. This for thruster is 1 kilogram or like that. However, I'm sure that this 1 kilogram is not the total propulsion system mass. So simply from this total impulse and specific impulse, you can calculate the required propellant mass. And if you calculate that amount, you will immediately find to generate this total impulse, you will need a 10 kilogram propellant mass. So the 1 kilogram this written on the data sheet would be the mass of the thruster head only. So propulsion system might be a 20 kilogram or something like that. And in the case of the fourth propulsion system, this was this one, and this was developed for Cubesat usage. And actually, the size is a 2U plus, and I could not find the mass, but I'm sure that it would be less than 10 kilogram. And in this case, you can install this Hall effect thruster for very small satellite like a Cubesat. So these are points of Hall effect thrusters. Basically, Hall effect thruster is suitable for high power operation, higher than 200 watt. But recently, less than 100 watt version is beginning to appear. So maybe future candidate. And also, please check it. This is a thruster head or propulsion system. Sometimes they describe thruster head volume or mass or those things. And also, this is very important, lifetime. This is not only for Hall effect thruster, but also for all of the electric propulsion system. Lifetime is a very important parameter. Because electric propulsion, its usage, so we assume a very long time operation for electric propulsion. Then we can utilize its performance. So lifetime is very important. So typically 1 month or 2 months or maybe 1 year operation is required for electric propulsion. So lifetime is very important parameter. Okay, next, ion thruster. So this is similar with the Hall effect thruster, but the difference is a higher specific impulse. And also, compared with Hall effect thruster, its technology is matured, I think. So you see, 4 thrusters I picked up here, all propulsion system were developed as propulsion system, not as a thruster head itself. So I could find the total propulsion mass and volume on the data sheet, please. So the difference is higher specific impulse and also lower thrust. So as I explained in the first session of this seminar, ISP and thrust, they have a trade-off relation. So if you increase ISP, thrust must be decreased. So compared with Hall effect thruster, ion thruster is increasing the ISP, but decreasing thrust like this. And they are developed for Cubesat. The power range is basically lower than the previous ones. And the propellant, yeah, you see the iodine propellant here. This is very high density and easy handling, good propellant. And in the kit is a traditional xenon. And also you will find the water ion thruster. Okay. So these are remarkable features. Yeah, compared to Hall thruster, its technology is more matured. And there are some lower power options like this, 40 watt. And you can find the propulsion system module. And again, lifetime is a very important factor. And there are several choices for propellant. Okay, we have remaining two thrusters, and one is this electro spray thruster. So in this thruster, they don't generate plasma. They directly extract ions from the liquid. And as a liquid, they are using ionic liquid. So very low vapor pressure liquid. And yeah, unique point of this thruster is this technology is unique to small size. So this is very different from previous examples. So far, all of other thrusters are miniaturization of standard propulsion system. However, electrospray and next field emission electric propulsion, FEEP, they are unique for micropropulsion. So basically, to extract ion from the liquid, they need very small structure, very thin needle. And that is compatible only for micropropulsion. In the case of standard size big propulsion system, this technology is not so adequate. So this electrospray and field emission propulsion system is, yeah, I can say that it's unique to small size. And due to that, I say that performance of this electrospray thruster is quite high in micropropulsion systems. Okay, and also, yeah, other feature is a high ISP. To extract ion from the liquid, they are using very high voltage. And due to that, it quite high specific impulse. But yeah, as a result of trade-off, thrust is going down. So in this case, less than 1 millinewton, like this. And also, you have to care of EMI, electromagnetic interference, because basically they are using very high voltage, like typically 5 kilovolt, and it's higher than ion and Hall thrusters. Okay, so final example, final type thruster is a field emission electric propulsion. So basically, acceleration principle is the same as electrospray. In the case of electrospray, they are using ionic liquid, but in this case, they are using liquid metal. But this and in the case of this liquid metal, its molecular mass is lighter than the ionic liquid. Ionic liquid has a very big molecular structure, so molecular mass is quite high. But in the case of indium, its molecular mass is lighter, and as a result, specific impulse is typically much higher than electrospray, and thrust level is going down fast. Okay, like this. So yeah, features are almost similar with the previous electrospray, and no plasma loss and high efficiency. And also we have to care of lifetime the electric EMI. And also I think especially this thruster provided by Propulsion, maybe I think this thruster would be the most successful micropropulsion in the point of sales. So already they have provided almost 100 thrusters for a lot of customers, and maybe 20 or 30 propulsion systems are flying in space actually. So a lot of flight heritage they have. Okay, so they are all the candidates that I wanted to show. But as you see, there are a lot of options, choices, and you may be confused to select the best one. And here, finally, I will give you one recommendation. So the amount of information is very important. I mean, not only the data sheet. They provide enough information for their customers. And I mean, so for example, are they participating in the conferences and publishing several papers? In that case, you will find much more information than dataset. So you may get more reliable information. So as I said at the beginning, for example, thrust or specific impulse, those information source is very important. Is it measured or calculated? And to find those, checking the information source is very important. And to select the propulsion system, please consider this kind of point. And also to check this kind of information, one good conference is a small satellite conference. Every year, this is held in the US, Utah, and here a lot of small satellite players are getting together, and you can get a lot of information. Additionally, they are providing presentations and papers on the web. So you can find the previous conferences information in this conference. So if you wanna easily get micropropulsion or small satellite information, please check this conference and its website. It's very useful, I think. Okay, so this brings the end of my presentation. Merci de votre attention. Thank you very much.
Thank you, Professor Koizumi. I think that was great. And the recommendations at the end, I'm pretty sure it will come in handy for some of the people here. So I don't see any questions in the chat. I don't know if anyone has any question. Either raise your virtual hand or post it in the chat and I will read it. Otherwise, I mean, I just have more of a, I mean, it's a curiosity more than a question. You mentioned the like equivalent propulsion system that your lab is working on, like for testing,
yeah.
but I didn't fully get like, can you explain a bit more what's behind it or what is it being used for?
Yes, this one. So
that one, yeah.
Yeah, we developed the same design propulsion system as a flight model propulsion system. So by using this, we can conduct operation training, and also if there is a trouble on the satellite, so actual flight model propulsion system, we may conduct troubleshooting by using this propulsion system on the ground. So we developed the same design propulsion system. So is this the answer of your question?
Yes, yeah. So it's basically a twin of what you have.
Yeah, twin. Yeah, that's great.
Nice. Okay. There's a question in the chat from Mathieu.
Mathieu, you can, I think, unmute yourself and unlock everything.
Okay, it works. Yeah, it was a question about the green propellants that you mentioned for one of the engines. Do you think there will be more spacecraft using these new propellants in the near future?
Yeah, I think so. Yeah. Yeah, especially in the case of small satellites, how to say, the merit of small satellites is quick development and easy development. And to utilize this advantage, we should not use a very dangerous propellant for micropropulsion system. So green propellant is very preferred for micropropulsion, but not only for small satellites, but also for standard size satellite. This green propellant, its shift is starting. So yeah, even ESA, NASA, or JAXA, somehow they prefer easy handling propellant. Actually, to handle toxic propellant, we need very costly facility and we need a lot of time. So by using this kind of green propellant, we can reduce the cost and the time to handle those toxic propellant. So I think this green propellant trend will go further in near future.
Cool. Any other questions?
Sorry for my kids sound.
It's all right. Okay, so if no one else has any questions, I think we can wrap it up here. Thank you again, Koizumi. Thanks a lot for all the lectures, and thank you everyone for joining. And until next time, thank you.
Thank you, everyone. Thank you, Kiro, for the time you spent on these presentations. Bye, everyone.
Bye.